Hello and welcome to episode 1 of Key for Problems. Today we'll be looking at problem 1 from the Project Euler problem set, which wants us to find the sum of all the multiples of 3 or 5 below 1000. So to start off, we can use the till keyword along with the argument of 1000 to create a list of all the numbers from 0 to 999, so it doesn't actually include 1000. And we can use the mod keyword to do the modulus operation, which essentially returns the remainder after being divided by the right argument. So anywhere there's a 0, it means it was evenly divisible by 3. So those are the multiples of 3. And then we can use the each right iterator, which essentially turns its left argument into a composition function, applying to each item on the right. So we can do this for 3 and 5 and see it returns us two lists. The first list corresponds to the modulus of 3, and the second one the modulus of 5. So now we just need to find for each of these pairs if there exists a 0. So we can do this using the min keyword. So you can see it will return the actual minimum pairwise between each of these, and if there's a 0, that means that it is a multiple of 3, 5, or both. So we can use the not keyword to flip the result and return us a true value wherever there is a 0 and a false value where there is a non-zero term, which then allows us to use the where keyword, which returns us the indices of all the true values, i.e. all the values that are multiples of 3, 5, or both. And all that remains then is to sum the result. And that is the answer. So this solution is quite simple, but it does have an issue that its time space complexity will increase if I was to increase the value here of 1000. So if I wanted to do on the multiples of 3 or 5 below 1 million, this would actually require more time and space. So it isn't the best performance solution. There is a solution that has constant time and space complexity, and it makes use of something called an arithmetic sequence. So an arithmetic sequence is a sequence of numbers that increases by a constant term. So multiples of 3 go 0, 3, 6, 9, etc. So each of those terms increases by 3 each time. Same with the multiples of 5. So these are perfect candidates for this arithmetic sequence. So the formulas are as shown. So the n formula is the nth term of the sequence, where a is the first term, d is the step in between, and n is the number of terms in the sequence. And Sn is the arithmetic series, which is the sum of all the terms up until the nth term, which is what we're going to make use of. So we can also make use of a edge case that we have in this scenario. That is that a and d are actually equal. So a being the first term, which is going to be 3 and 5. We could start at 0, but 0 is not going to contribute to the sum, so we may as well start at 3 and 5. And d is the step in between, which is also 3 and 5. So those being equal, we can actually sub a n for d in the n formula and simplify an to just a times n. And then if we sub that into the Sn formula, we can also simplify it. So if I return now to my KX developer, and this is the actual formula that we were able to, the simplified version of the formula. So it is 0.5 times n times a times 1 plus n. And remember, q operates right left, so this will be done first and as come on. So we don't actually need the brackets here. So you will notice something interesting is that I did change, instead of dividing by 2, I did a multiply by 0.5. So the reason for this is, number one, it makes things nice and neat, as we can write this in train form rather than having to, put this part in brackets and then have a, divide by 2 on the right hand side. But also, it is well known that division in most modern CPUs is actually slightly slower than multiplication. So this can be demonstrated here. I'm just going to run this. This is a performance function I have created that essentially runs each of these expressions this number of times. So if I run this, you can see here, now we are talking about nanoseconds here, so the difference is not, huge, but there is a slight difference. And, if you were going to be running these things, these kind of operations, millions and millions of times, it will eventually add up to a significant difference. So it's just something to be aware of. So returning now to our arithmetic sequence solution, we to actually calculate this, we essentially need to define A and define N. So A is the first terms in the series, or the sequence, which is going to be 3 and 5. Now Q is, we're going to do this in a vector form, i.e. we're going to do 3 and 5 simultaneously, because Q operates in vectors. And N is the number of terms in each of these sequences. So we have the numbers up until 999. So how do we find how many of those multiples of 3 and multiples of 5 are going to be in between 0 and 999? Well, it's actually quite simple. It's just to divide 999 by each of these numbers. So you can see there's 333 terms are going to be divisible, or multiples of 3 between 0 and 999, and then there's going to be 199. So the 0.8, of course, we can't go up because we can't include the 200th term, which would be 1000, because it's not included. So we can get rid of that just using the floor operator to round down, or the floor keyword, sorry. So we essentially have our A and N defined. So if I run this, you can see this is the arithmetic series for 3, and this is the arithmetic series for 5. So all I should have to do now is just to sum these both. But this does not agree with the actual solution. This is the correct answer, which was given before this solution. So what is actually wrong here? Well, what's actually happening is the arithmetic series is double counting the multiples of both 3 and 5. So say the number 15 is a multiple of 3 and 5. It's going to be included in this series, but it's also included in this series. So when we sum it together, it's actually being double counted. So how do we remove that? Well, the multiples of 3 and 5 are themselves will form an arithmetic series. So what are those terms? Well, they're actually just going to be a series starting with the product of these two numbers and then increasing by that same amount. So I'll just make a slight modification here. So this is the join assign operator, and I do the product of the previous. So the product, of course, is 15. So I'm going to join 15 onto this list. So our sequence then is going to be 15, 30, 45, etc. We're just going to do exactly as we've done for 3 and 5 and calculate the arithmetic sequence for this, arithmetic series, sorry, for this, but we're going to subtract rather than add, just to remove that double counting. Now, there is one thing to note, is that because we want to subtract, we should make this a negative number. However, when we're working out n here, n is the number of terms, which must be positive, so we just need to add an absolute in here to keep this value positive still. So now when we do this, you can see now we have the 3 arithmetic series for these 3 numbers, and if we do the sum, yep, and you can see now if I run the previous solution, you can see these results match. So the actual performance then of these solutions, so I told you this one was constant time, whereas this one increases with n. So if I just go over to my other scratchpad here, so I've put both of these solutions into functional form. S1 and S2, and I have the timing function, as I showed you before, just runs each of them for this number of times, but this memory use also will measure the actual memory requirements. So if I change this to 1099, sorry, let me just change this to X and change this first. So define this, and if I run this, so this is running 100,000 times each, you can actually see that S1 is much less performant in terms of time. So the average is a lot more. And if I look at the memory, you can see as well that S1 has greater memory requirements. Now, if I was to, as you've seen there, I have this increase this to say 100,999 or 99,999. And run the memory again, you can actually see now that the memory for this is really increased, but the memory for this is still constant, still the same as it was for those lower numbers. And if I run the, I'm just going to take one of the zeros out of this because it might take a while to run, or two of the zeros, just do 1,000 times. It's just really to get a good average. You can see now that this has grown massively, but this isn't much different. So yeah, please let me know what you think of the solution, and if you have any solutions, that are interested in more performance, or just any kind of solution, just share them below in the comments. And thanks for watching.